tell you about exoplanets. So exoplanets, I will define it briefly now, and then we'll really dive into it. These are planets that orbit stars other than our own sun. And something that I spend a lot of time thinking about is how we can do a better job directly studying exoplanets. So literally taking pictures of planets orbiting stars that are not our own sun. So, like a roadmap for this talk, we're going to start out by thinking about what exoplanets are. We'll kind of motivate why we might want to take pictures of them so that we can study them in detail. We'll explore how we do that and what kind of technology we need to take pictures of exoplanets. And then I will tell you about one project that I've been working on a lot lately, which is building a new instrument to do a better job characterizing planets. So the background image on my first slide is an artist's impression that is just intended to convey a couple of things. One is that we now know of many, many exoplanets. The current tally is like just short of 6,000 or so. And the second part is that there's a huge diversity in the population of exoplanets. This is just an artist's impression, but it kind of encodes the fact that there are lots of different planetary compositions and masses and orbits that are much more diverse than our own solar system. And so something that people spend a lot of time trying to do is to take the population of exoplanets that we know of and understand like the physical processes that could form such a wide range of exoplanets. So what do I mean when I say exoplanet diversity? There are like many ways to look at this. I really like this diagram. This is kind of halfway between an artist's impression and a real scientific chart. This is showing you little sketches of what we think the kind of types of planets are for a couple of hundred known exoplanets. So these are not photos of the planets. These are just an artist's drawing of each planet based on how big we think it is, how massive we think it is. So, you see things in here that look kind of like Jupiter and Saturn. You see little guys that are more like, Earth, Mercury, Venus, Mars. So that's what you're seeing in the pictures here. These are spread out in a space that shows you temperature going vertically and density going horizontally. So if you look at this, I've given you some numbers, but I've also given you little pictures to like understand like what we're talking about when we say the average temperature of what these planets are. So we know of planets that are as cold as Antarctica. So if you have good eyes, you might see that these are little penguins jumping into the water here. We know of planets whose average temperature is about the same as the boiling point of water. We know of planets that are as hot as Bunsen burners. So there is just a huge range of conditions on our exoplanet population. And their compositions also vary greatly. So over here, this is average density of your planet. Water is right around here, so 1 gram per cubic centimeter. You can see rock, like granite-ish over here. Things like iron are over here, and even gold. And so there are also a wide range of just like average compositions of these exoplanets. One thing that was not on this figure, because it got made a while back, is that there are actually planets that are about as dense as cotton candy. So I like to throw the fluffy stuff picture over here. Those are called super puffs. And they're very low density, really puffy planets. And so, there are many different ways that you can study exoplanets, and Lauren kind of alluded to this, and that, there are lots of different techniques that you can use to try to understand their properties. But one important piece of doing that is actually collecting light from the planets themselves so that you can study it in detail. And we'll think more about that in a second. The only way that you can do that is by actually separating your planet light from your starlight and recording it. So that's called direct imaging. We're not going to look at a ton of like plots in this talk, but this is one of them, and we'll look at maybe one more. This is just showing you the total number of discovered exoplanets as a function of time. So this shows you how many we know from the very beginning when we discovered the first exoplanets in the early 90s. All the way through to, I think I pulled this a couple weeks ago. This is a pretty current count. We can see that the current tally of confirmed exoplanets is somewhere around 5,800. And the vast majority of these were discovered using what are called indirect techniques. So what this means is that rather than like taking a picture of the planet itself, you're observing the planet's effect on its star. And so what that can mean is you can say, like, oh, I'm going to look at the brightness of the star, and it looks like it dims every once in a while because the planet is moving between me and the star. That's like one example. Another example is that your star looks like it's wobbling because of the gravitational tug of the planet. The color coding here tells you what techniques were used, and I'm not going to like go through the list of those many techniques, but I will say that those two methods that I just mentioned are the green and the purple bars. So those are all the indirect planets. What we're going to focus on for the rest of this talk is one of these tiny little slivers that shows you the number of planets that we've actually taken pictures of.
So the green is for the like illusion, and
the other way around. So the purple, yeah, and I should have said that. So the purple ones show you the dimming thing that I mentioned. So that's the transit technique, and the green shows you the wobbling. And so that was actually a very productive early method, which you can see. So we want to take direct pictures of these planets. I will just take a couple of minutes to hopefully convince you that this is a worthwhile thing. Something that you might infer from the plot that I showed you on the last slide is that we have very few directly imaged exoplanets, meaning that it's really difficult to do. So like it takes a lot of effort to do this. We're just starting to get really good at it. Why are we putting so much work into it? And there are many different ways to answer that question, and one that I like to think about is thinking, what can an alien astronomer learn from Carl Sagan's pale blue dot? So you might have seen this image. So this is a very famous image from the Voyager spacecraft called the pale blue dot. Voyager is a spacecraft that we sent to the edge of our solar system and then beyond. When it was leaving our solar system, it turned around and took a picture of the Earth. And so this dot right here, this is the Earth, seen from the outer regions of our solar system. And so this is like still inside our solar system, and it already looks just like a blob in a picture. And that's like, you know, there's some things that are very profound about that. And I would recommend going and looking up Carl Sagan's quote about the pale blue dot, because, you know, one of the things that you can think about this image is that everything about our Earth that you could observe from like light is packed into this little blue dot. So if you could like collect the light from the pale blue dot and study it, then you could learn many different things. The method that we use to do that is called spectroscopy. And what this involves is you say, all right, I'm going to collect the light that's coming from my planet or my pale blue dot, and I'm going to send it to something like a prism, and I'm just going to spread my light out according to its color. So this is something that you might be familiar with. You know, they have these like really pretty like window ornaments that make little rainbows on your wall. Basically a fancy version of that. You can collect your light and spread it out by its color or its wavelength, and then you can study how bright it is as a function of its color. And if you did that and you took a picture of it, you might see something like this. This is showing you that you've got red light up here, blue, purple light down here. You can see it kind of wrapping as you're going down the image. So this is showing you how bright your object is as you decrease the wavelength of the light moving down. And you might, if you have sharp eyes, notice these little vertical lines here. That's where there is missing light because of whatever is making up the atmosphere of the thing you're looking at. So just because of really like quantum mechanics, different molecules and elements will absorb different wavelengths of light, and all of that is imprinted in the light from your pale blue dot like a fingerprint. And so you might record an image like this. I've cheated a little bit here because this is actually the spectrum of a star, not a planet. Planets are going to look a little bit different because they have more complicated molecules. But you can then turn it into just kind of a line. So you say like, how bright is my object as I change the color of the light? And this is what it would look like for the Earth. So this is the last really, science-y plot that we're going to look at together. So if I took a spectrum of the Earth and I said, I'm going to change the color of my light, how bright is the Earth? It would look like this. And you see all of these bumps and wiggles here. And because of really nice lab measurements that we have, we can connect these bumps and wiggles to specific molecules in Earth's atmosphere. So just as an example, you can see oxygen, which is great for breathing. You can see ozone, which protects us from high energy radiation from the sun. You can see water vapor, which tells us that maybe there are oceans on the surface of the planet. We know that there are, but you can imagine being your alien astronomer. You might say, oh, look, water vapor. Maybe there are oceans. Carbon dioxide can be produced by, life on the surface of your planet, and so can methane. So if you could record a spectrum of an exoplanet, you could spread the light out and look for fingerprints like this and learn something about what the atmosphere of your planet is made of, and maybe even whether there's life on its surface. So that's the big picture motivation for why we want to do this. Heading toward characterizing Earth-like exoplanets is like the big picture goal for the next couple decades of exoplanet astronomy. I will say right now that where we're at currently is we can do this for planets that are a lot like Jupiter. So we're working our way toward Earth. We're working with giant planets, and we're hoping to get down to lower masses in the future. So that's the why. How do we do this? So we're going to focus just for a little bit on some of the technical things that we need to take good pictures and spectra of exoplanets. And we're just going to explore two things. One is resolution, so how sharp our images are, and the other is contrast. So we need to be able to look for a faint planet in the glare of its star. We know that stars are really bright, like the sun is really bright, not super bright in the grand scheme of stars, but still much brighter than any planet. And so we need to be able to deal with that. So we're going to start off with resolution. So we need high resolution. I like to use my friend Jake to explain this. So we're going to imagine that we're Jake, my dog, and we have a little telescope, and we want to take a picture of a planet around another star. So we have all dealt with resolution in this context, or not in this context, but like this before, in that if I took a small object and I looked at it here, I could see it really well, but if I put it across the room, it would be really hard to see. Same thing. Let's imagine we have Jupiter orbiting the sun, and we want to take a picture of it. If it's really close, Jupiter orbits the sun at something like 500 million miles, so that should be really easy to separate the starlight from the light from Jupiter. But space is really empty, and these stars that we do this for are actually really, really far away. So how far away are they? If I'm going to tell you in astronomy units, it's something like a few hundred light years. It's hard to find meaning in that, so we're going to make that more meaningful. If I want to tell you in miles, it's about 3 quadrillion miles. So now we're working with a unit that we're comfortable with, but that's like a huge number. So what does that actually mean? I'll give you an analogy. What does high resolution mean? It's like, imagine we put Jake up here with us at Lick, and he wants to take a picture that is like the kind of resolution we need to take pictures of exoplanets. That would be like if he sent his friend Finn down to Hawaii, so like 2,300 miles away as the crow flies, and took a picture of Finn's face when Finn was sitting on the top of a mountain in Hawaii. So this is hard. This is really difficult to do. If this isn't doing it for you, another way to think about it is you're trying to take pictures of things that are about 10,000 times smaller than the full moon. It's really, really small. Oh, and yeah, Finn's not happy to be up on the mountaintop for this experiment. Okay, so that's high resolution. How about contrast? So how faint are planets compared to their stars? A good, easy-ish to image giant planet would be something like 1 million times fainter than the star that it's orbiting. So for a real-life analogy there, that's like trying to take a picture of a firefly next to the Pigeon Point lighthouse. So super hard to see in the glare of the bright star. So we need to accomplish these things. We will talk about how we do it, and then we'll get into the specific project. In general, our starting point needs to be a really big telescope. So why is that? That's because a bigger telescope means a better view. This is just because of how light interacts with optics as it moves through a system. The bigger your lens or mirror is, the sharper your image is going to be. So luckily, we have big telescopes. UC astronomers are very fortunate to have institutional access to the Keck telescopes. So that's what you're seeing here. These are two 10-meter telescopes, 10-meter in diameter telescopes on the big island of Hawaii on Mauna Kea. And so I just want to pause for a second and draw a little circle for you here. So that's an SUV parked at the bottom of this building. So these are really huge facilities. Like a lot of work goes into building and maintaining them, and a lot of work goes into using them to do research. We're very lucky to get to use these to do this kind of science. So this is great. We have a big telescope. We know that big telescopes, in theory, should get us sharp images. And so our theoretical picture is like Jake, the Chihuahua over here, small dog, he's a small telescope. Small telescopes produce relatively blurry images in theory. So you might take a picture of a star, and instead of seeing a nice sharp point, you would see like a disk that's like got a finite size. If you had a big telescope, so Finn's a big dog, he's got a big telescope, in theory, you should be able to separate the starlight from the planet light because your images are sharp. They're not as blurry as what you would get from a small telescope. So this is great, we've solved the problem, but there's a new one, which is that stars twinkle. So twinkle, 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 little star, like twinkling stars, they're pretty because they're twinkling. Astronomers hate the fact that stars twinkle. And the reason for that is because what twinkling is it's actually Earth's atmosphere blurring the light from your star. And it changes it on really fast timescales. And in fact, if you had a 10-meter telescope and you didn't do anything fancy with it, you would end up with about the same blurring as you might expect through like a 20-centimeter small telescope just because of the Earth's atmosphere. So we need to fix that. Just because it's interesting to look at this, if you could take a really fast image of what Earth's atmosphere is doing to this starlight, you would see something that looks like this. So what you're seeing here is all of the different ways that Earth's atmosphere is bending the light from your star. It's spreading it out, and it's changing on timescales that are like multiple, like 10 to 100 times a second. So this is a problem. If you took a longer picture, it would average out into this fuzzy blob. So we need to untwinkle the stars. Lick Observatory is actually a very special place because a lot of the technology that we've developed to untwinkle the stars was tested out and demonstrated here when it was very young. So what is that technology? It's called adaptive optics. And this is a technique where you measure how blurry your starlight is. You calculate what you would need to do to a mirror to unblur your light. And you actually deform a mirror very quickly over and over again to do that correction. So these mirrors are called deformable mirrors. I'm showing you a couple of examples over here. They can have a range of sizes. They can be as small as a penny and be like really close to your camera in your setup, or they could be like the second mirror in your telescope. And there are different reasons why you might want to use each one. I like showing this one because what you can see here, all these little circles are the points where you would push and pull on your mirror. And so you're literally just crinkling a mirror, something like tens to hundreds to thousands or 1,000 times a second to correct for this blurring. And so now our fast video would go from something like this to something like this. This is much more compact. Now what you're seeing are these rings that are caused by just the fact that you have a circular mirror. So this is like intrinsic to your optics. And then there's some leftover errors. You can see those little blobs kind of dancing around. This is way better for looking for faint things, because you imagine if you had a planet here, it's much easier to see than one that's in this noise. So that's adaptive optics. I will show you some examples of using adaptive optics to image exoplanets, but it's been used for many things at Keck and here. Here's just one really pretty example that I like to show. There are lots of astronomers who use adaptive optics to study solar system objects. This is what you would see for Saturn and Uranus, for example. Before and after you turn your adaptive optics system on, things get much sharper. You see images that actually rival Hubble when you do this. Same deal over here. You can see after adaptive optics and before. And these kinds of observations allow solar system astronomers to do things like monitor storms on the surfaces of these objects, and volcanoes too, and we'll come back to that. So, thanks to adaptive optics, we can now directly image and characterize giant exoplanets. And when I say giant, I mean Jupiter-ish like. They're like as massive as Jupiter. They tend to be hotter because those are brighter and easier to see. But this is a system called HR 8799. This is the first directly imaged multi-planet system. So I will explain what's going on here. This is a time-lapse, collection of observations of this system spanning several years. They have all been processed to remove the star. So we've gone through and subtracted the star using post-processing, and you can see 4 planets here, 1, 2, 3, 4, and we can actually watch them orbit around their star. There's some leftover noise here, and a lot of work goes into writing software to mitigate that noise. But once we have images like this, we can start to say, okay, this light definitely only comes from the planet. I'm going to spread it out and measure how bright it is according to its color, and then look for those little fingerprints that we talked about earlier. So for the rest of this talk, we will think about an instrument that I've been working on with many other people to do this for a wider range of planets, and that's called SCALES. This is an instrument that is getting built for the Keck telescopes right now. It's getting assembled at UC Santa Cruz. It's going to ship out to Hawaii at the end of this year, beginning of next year. And then it's going to take pictures of colder exoplanets than the ones that we've imaged so far. So I will tell you what the acronym means in a second. First, I'll just tell you what this instrument is. It's an instrument that gives you simultaneous imaging and spectra. So basically, the way to think about a SCALES data product is you have an image at a whole bunch of different wavelengths, and you get that by kind of picking off different points in your image and spreading the light out with a prism. SCALES is going to operate in what's called the thermal infrared. So this is longer wavelength light than what our eyes can see. It's kind of like night vision goggles. So that is part of what makes it sensitive to cold planets. So I'm the SCALES project scientist, which means that a lot of my effort goes into thinking about whether SCALES can do the science that we want it to do. And so something that I do as part of that process is simulate what we think we might see through SCALES. And here's a simulation of the inner 3 planets in that system we were just looking at, observed by SCALES in something like an hour. And it's going to be routine to find these hot giant planets. So this is great. This means that we're going to start off in a position to, easily measure things that we've already been measuring, and we're going to push down to more challenging systems. All right, so we'll spend a little bit of time just talking about how SCALES works, because I should tell you what the name stands for, and there are some terms in here that we're going to define. So SCALES stands for Slicer Combined with Array of Lenslets for Exoplanet Spectroscopy. So it's a mouthful. So I'll tell you what it all means. So we're going to start with something that's really fundamental to SCALES, which is that normally, you take a picture and light from different points in your field or, in the sky lands at different points on your detector, and you've got your image. One thing that's unique about SCALES is that rather than doing that, you focus your light onto what's called a lenslet array. This is, imagine that each of these little squares could be a pixel in an image. Instead, it's a tiny little lens. So you're picking out the light from different points, for example, under your star or under your planet, using these lenses or lenslets, which we call them. And then you're sending that light to a prism, it's your array of lenses, and you're making a spectrum for every point in your image. And so the actual images that we would record from scales would look something like this, where each one of these little diagonal lines is one spectrum that goes with one point in your field. So what does this get you? It gets you an image that you can then process and turn into your little cube of individual images at different wavelengths. So I think yeah, there we go. Got that in there twice for some reason. There it is. So processing that gets you this kind of cube where you can then say, oh, I know how bright my planet is at this wavelength compared to the other wavelengths. And then you can actually look for signs of molecules. One thing that's exciting about scales is it's going to push us by a factor of a few down to colder planets than the ones that we can currently image and characterize. And so here's kind of a fun simulation, again, where we've removed the star, where you can see kind of the edge of what we might be recording with scales. You can see here a really cold planet kind of coming in and out. And this is a much longer observation, simulated observation. So something that we're doing right now is planning early science with scales to happen sometime in the first half of next year, where we actually demonstrate the kinds of planets that we can image and characterize. There's lots of things going on with the instrument development right now, because we're like less than a year away from actually shipping, which is really exciting. And so I wanted to show you kind of like our picture of what the instrument was going to look like a few years ago, and that actually turning into like real physical things. So here's a little drawing of what the inside of the instrument would look like. There's some lenses, there's some prisms over here, some filters that isolate certain colors of light. This is all going to be contained in what's called a cryostat, because our instrument needs to stay like really, really cold, because we're working with long wavelengths of light. The size of this cryostat is about 6 feet this way, 3 or 4 feet this way, and 4-ish feet this way. This is a big instrument. It weighs several thousand pounds, and we're currently putting it together. So this is kind of an old picture, but I like to show it because a couple of years ago, we actually 3D printed a model of scales just to like understand where everything would go. This project has a lot of student involvement, and so here's one of our former UCSC undergrads, who actually did a lot of the 3D printing for this, and a lot of machining for the instrument with these different parts. And the one thing that is up and coming that's really exciting is actually another piece of the acronym. So now we're going to talk about the slicer. So the goal of scales is to get us spectra of exoplanets. I showed you those little short spectra, the diagonal lines before. The slicer is actually going to enable really detailed study of exoplanets when you combine it with the lens slit array. So just real quick, what an image slicer is a set of optics that's going to take certain lenses, the images made by certain lenses, and allow you to spread the light out in much more detail. So instead of this before, where we have these short spectra, we're going to take a subset and spread them out way across our detector. So we get really fine information about the color of the light, and then we can look for signs of molecules like methane and ammonia and water vapor, carbon monoxide, carbon dioxide. And doing this is going to require us to kind of steer our planet light into a particular location in the instrument. So we actually have mirrors that move really, really small amounts in these cryogenic environments to take planet light and move it onto the right region of our detector to do this. All right, so that's defining the acronym. Now we'll look at some pictures for the rest of the talk, which I think is really exciting. So where we are in the process is that basically almost everything has arrived, everything has been ordered. Here are just some examples of the optics that are getting installed inside scales. So these are pictures of filters. They're all like about this big. These are going to get installed to isolate certain wavelengths of light. There are many optics that are going to go into the cryostat to rearrange the light in the way that we need it to actually do spectroscopy. Since we're in the infrared, these are actually all gold-coated, which feels very fancy to be around them. And every time we get a piece of the instrument, we have to test it to make sure that it's going to do what we want it to. And so here are a picture of a couple of UCSC grad students who have been helping with this, and they're actually measuring the surface roughness of one of the optics that we got. And so you can see, nothing is going to be perfectly smooth. They measure some, kind of like ridges across the optic. These are within what we're okay with for this optic. They also have tested the little mirror that we're going to use to move our planet light around in the instrument. You can see it going into a small cryostat over here. And what we can do is cool it down and then look through this window to see whether it's moving the way we want it to. So almost exactly a year ago, the actual Scales instrument enclosure or cryostat got delivered to UCSC. This was a really exciting day for all of us because the instrument shops on campus are on such a steep driveway. We had to have like a specialized forklift show up and like a rigging team come in to deliver this thing. We showed up at 5 a.m. to meet them there. It was like honestly kind of terrifying to watch this go into the building, but you can see it on the forklift here. And this is it getting rolled into the clean room at UCSC. So this box weighs a few thousand pounds once you fill it with everything. And you can see them positioning it in the clean room. I don't think I have the entire process in this video, but they put it within like an inch of where we asked them to. So they're very talented riggers. Yeah, so there it is. There's everyone with the cryostat. So this is just a very small fraction of the instrument team. There are dozens and dozens of people who work on Scales. And you can see the rigging guys here and here. And this was about a year ago after the cryostat delivery. And so since then, we've actually been installing all of the pieces of Scales and then testing them out in this box. So here's a fun time lapse of us taking the lid off the cryostat. So this weighs something like several hundred pounds. And so we have a whole procedure for taking it off, mounting it on a custom rack so that it can sit in the clean room. And then what you're seeing down here is what's called a radiation shield. So this protects the inside of the instrument from heat and light that could cause noise. This is what it looks like when you open it up before anything is in it. So this shiny surface here is called the optical bench. And if you have sharp eyes, you might see these little dots here. Those are all bolt holes to install things on the bench of Scales. And we started to do that. And we've actually started to close it up and cool it down and test out these optics. You can see one of our engineers here, Christian, installing different 4 optics where we're following the light path through the instrument. We can make sure that these are aligned. Here's a more recent photo with more stuff in it. So this is where the different dispersers like prisms are gonna live. You can see some different optics here just for alignment purposes, and then you can see some cables for things like electronics going in. So over the summer, we're gonna close up Scales a few more times and put everything into it and then continue to test it and make sure that it's gonna do what we want it to do. It's gonna ship out to Hawaii by the beginning of next year, and then it'll see light shortly after that and start doing science. So in addition to taking pictures of exoplanets, it's going to do a wider range of things. It's also going to be useful for the same kind of solar system science that I showed you before. One cool example is monitoring the volcanoes on the surface of Jupiter's moon Io. So we'll be able to see how their brightnesses change, both with the color of the light and with time. So you can see those dots here are our little simulated Scales observations of volcanoes. It'll be useful for catching actively forming planets in what are called protoplanetary disks. These are disks of dust and gas around young stars, and we can resolve them with Scales and study how bright they are and whether there are planets orbiting in them. And we'll also use it to take pictures of the remnants of dead stars, so the clouds of dust and gas that remain after a star goes supernova and explodes. Lots of exciting stuff to look forward to with Scales. Where are we headed big picture? We're going to get down to these cooler giant planets with current generation telescopes and instruments. But to really get down to Earth-like planets, we're going to need bigger telescopes. So we're going to work on the next generation of telescopes that, at least from the ground, are going to be a few times bigger than Keck. With those huge diameters, we'll be able to take fine pictures with high sensitivity so that we can actually record light from Earth-like planets and do things like try to find the exo version of Carl Sagan's pale blue dot. Maybe we can find signs of life on a planet around another star, which would be really exciting. So I will just leave you with the thought that the future of direct exoplanet studies is bright. I'm happy to take any questions, and thank you so much for your attention.
Great. We do have time for questions. Yeah.
How much does it cost?
Oh, that's a great question. There are different answers depending on how you count, but like a good ballpark is something like $7 million. Yeah, not the worst thing. Yeah. Yeah.
Yeah.
Is there anything special about the location of Hawaii? Like, why are we moving it over there?
Yeah, that's a great question. So, especially for infrared astronomy, it's important to be at a site with conditions that allow you to first get above a lot of the atmosphere. Because one thing that I didn't mention that's important for all of these observations is that Earth's atmosphere has its own molecules in it that are going to absorb light and emit light and like imprint themselves on the data. And so getting up above a lot of atmosphere is important. So Mauna Kea on the Big Island is really high. So that's one thing. But beyond that, you want dark skies and also weather conditions that are like amenable to like observing many nights a year. So Hawaii is relatively unique in that it can offer that nice combination. Yeah. Yeah. Great question.
How about in the back?
Are you taking some images from satellites as well? Or are you images coming from satellites?
So for scales, we're always imaging from the ground. So for scales specifically, the images that it's going to take are all just coming from the Keck telescope. But that said, like there's a lot of complementarity with space-based observing. So one example of that is that there's a satellite called Gaia that's going to measure. It is measuring the positions of many millions of stars to really high precision. And it's going to detect like the wobble caused by planets, and then Scales is going to follow up like a subset of those Gaia detected planets. That's one example. There are some interesting projects going on at Keck that kind of combine satellites with ground-based observing. There are some ideas for like putting a laser out in space to act as like a guide for the adaptive optics system that would involve like a lot of interaction between the telescope and a satellite, but that's like it's not something that's happening right now. It's more in the concept stage.
In terms of adaptive optics, how do they actually react to the light as it seems like you need to know the spectrum in order to alter the spectrum to get a good image?
Yeah, that's a great question. So what you do, so the like, you know, kind of catch-all term for this is a wavefront sensor. So there you can design a system that compares the incoming light to like a perfect reference. So you can basically manipulate your light and compare it to something that you know is going to be not blurry at all. And then you can compute how different your light is from that reference and then send commands to your mirror. And you do that in a loop that runs like hundreds of times a second. Yeah.
One has to do that by shooting a laser next to where the telescope is pointing. So you know exactly what the laser is because you're literally generating it. And any effect on the laser has to be from the atmosphere.
Yeah.
Yeah. Go back here.
Is the array part of the Scales instrument effectively a Fresnel lens?
You know what? That's like a really great way of thinking about it. So it's like the lenslet array itself. Like the reason why it's called a lenslet array is because it's a piece of silicon that's been etched to have a whole bunch of square lenses on it. So each individual one behaves like each individual square behaves a lot like a Fresnel lens. It's not exactly a Fresnel lens, but like it's an array of mini lenses. Yeah. Yeah, that's a great question. So there is a lot that we can do from space, and the thing that we can't currently do is take high resolution pictures like the ones you could get from like a 10-meter telescope, just because the space telescopes are smaller. So there's like this different, in order to get a sharp image, you need a big telescope diameter. If we could, put like a 10 or 20, 30 meter telescope out in space, then we'd be done. There are logistical problems that make that like really expensive, and that and then they're difficult to maintain. So there are certain planets that James Webb and future space telescopes are way better at finding, and those are the dim ones that are a little bit wider out from their stars. And then the ground-based parameter space is the stuff that's closer in, that's a little bit too close for the space telescopes to find. But it's certainly true that from the ground you would have a much harder time finding the really, really faint ones. Yeah, so they can be used together. Yeah. Great question. That's a great question.
But we're going to be here afterwards to ask the rest of the questions we don't get to.
Yes.
And I see a hand in the back there.
That is a great question. Yes. So for some stars, after your star goes supernova, what's left is a black hole. Whether or not that happens depends on how heavy your star was in the first place. So a good rule of thumb is that a star that's going to do that is going to be several to like 10 times more massive than the sun, closer to 10. Yeah, definitely not less than 8. Yeah. That's a great question.
We're going to be here to answer more questions, but for now, join me in thanking Dr. Sallum.
Thank you.
Thank you, everyone.